So, hello everyone, and welcome to the live session. I hope you all are doing good. And today is our lecture number 5 for this week. But this topic we have continued this topic from the last week. So I think this might be lecture number 8 or 9 because last week the first lecture was not conducted. Rest we are in continuation. I hope you are following this complete lecture series from starting so that you can get a connect how the topics are related in reaction mechanism topic. So our aim was to practice questions on the basis of what we have learned, but since few important parts are still left of the NGP reaction, and it's very important. So first of all, it become important my responsibility so to make your content part strong so that you can practice your questions on your own also. So for this lecture, I will be explaining you little more. I will be focusing little more on the theory part, and if time permits, we will of course solve the previous year questions or some practice questions also. So welcome to the live. Good morning to each one of you, and let's start the session. Good morning, Manisha. Good morning, Om Arya. Good morning, Pooja. Good morning, Praful. Good morning, Mosmi. Good morning, Rani. I hope you all are doing well. And let's start this session. Those of you are who are seeing this video for the first time, or you are very new to the channel, we have started our reaction mechanism series, and for this week we have reached to our lecture number 5. And today's part, first of all, we will be covering the left off portion of SNNGP mechanism, because this is one of the most important one, and of course the questions are asked in any exam, be it CSIR NET, be it GATE, be it IT JAM, or any other exam. This particular mechanism holds a great importance, and we are about to finish this mechanism. So first of all, I will focus to cover the concept. Good morning, Jay. Good morning to everyone. So first of all, let's take a recap what we were studying in the previous lecture so that we can get connected to the topic. Moving ahead, we have done with the spinase rearrangement. I have discussed the NGP part. In the yesterday's lecture, we were talking about the case number 4, where we have a Norborane system. In a Norborane system, we learned that yes, there are three types of these intermediates which can be formed. Very famous non-classical carbocations are formed, and these non-classical carbocations are actually an example of three-centered two-electron bond. We have gone into a very detail of this topic so that a question, if question is from the depth of the topic also, then also we are able to solve the question. This is what Claydon says. It says that from the substrate, or we can say from the living group side, the sigma star orbital is involved, and from the alkene side, the filled pi orbitals are involved. This is what we have discussed in the previous lecture. I have discussed few questions also, how CSIR net asks questions from these topics like SN1 and SN2. Moving ahead, we talked about how the product formation can take place, and we have done some questions of how the rate comparison can be done in the cases of Norborane. We find that for the first scenario, the rate comparison was very easy, but it sometimes become difficult to form the product. So for the second case, the actual product is where a sigma bond NGP is taking place and enchimeric assistance of sigma bond is taking place, and the product is looking like this, which we have drawn into the circle. Moving ahead, we have seen that we need to compare the rate here. We have compared these questions, these rates also. Now, at the end of the lecture, I left you with a homework question where we need to compare the rate of all these 3-4 substrates towards the NGP reaction. Can you tell me in the comment section what is your answer so that we can finally match our answer, and let's find whether you have done it correctly or not. You have a 3-membered ring, you have an alkene system, you have another 3-membered ring system. See, this type of question I think was once asked in a GATE exam also. If you remember, I remember nearly in 2020 they have asked, but this was not the exact question, but related to this they have asked. Good morning, Diksha. Be quick, tell me what is the rate order according to you, which has the fastest rate and which has the slowest rate in these 4 substrates. You have a three-membered ring situation. Yes, we have dealt with a three-membered ring example in the yesterday's lecture also. Mosumi is saying, sir, 4, then 1, then 2, and then 3. Very good. Anyone else? According to you, Mosumi, it means an alkene is going to have a faster rate as compared to a three-membered ring. Okay. Please do share your views. What is your answer? 4, then 2, then 1 and 3. Okay, Om. 4, 2, 1, 3. Very good. See, first of all, the rate for a three-membered ring is very high. Why? Because any ring which is present in strain wants to release its strain, and if you allow it to release the strain, the rate of the reaction will be very fast. It is going to be extremely fast. Now we have two three-membered ring scenarios, one in the case of K2, and if you carefully look, we have also a three-membered ring present in this Normoran system. And in the fourth system, this three-membered ring is at the bridgehead center also. So it is very much in strain. So what happens is, these sigma electrons present into the bond attacks into the sigma star orbital very fast so that they can release the strain very quickly. That's why when we compare the rate, the K4 is going to have the highest rate, no doubt. Now we come at the second scenario. Again, in the case of K2, we have a three-membered ring. Since this sigma bond attacks into the sigma star, again the strain of the ring is released. So this type of rate for attacking into sigma star of the OTS is going to be very fast. So the second is your K2. It means after K4, the rate will be high for the K2. Now comes the normal situation of an alkene, where alkene attacks into the sigma star orbital and the OTS is removed. So K1 lies here, and of course K3 is going to be this with slowest rate because it does not have any pi bond for the n-chimeric assistance. Do you understand this order or not? Is it clear, Jay? Jay, you are telling me that third is going to have the highest rate. Third is going to be higher. This is completely not digestible for me. In we have also compared in the yesterday's question about K1 and K3. So it was clear enough that K1 is going to have the high rate as compared to K3. Then how you are answering that third is going to be have the highest rate? Okay. Good morning, Ankita. Clear? Very good. So these type of questions are do asked in your exam. So take care of these type of questions, and you need to practice previous year questions on this concept. Okay. So we have dealt with these concepts. Now moving ahead, there are few more questions, but I am leaving those questions for now. We will be taking that into some practice sessions. Moving to the next part, that is the miscellaneous part. If you remember the NGP mechanism, when we have started, we have distributed this NGP into few cases, where case number 1 was for the acetylysis reaction, case number 2 was for the phenyl ring when present as a neighboring group, case number 3 was of bromine and a OH group present in a molecule, and the fourth case was for a non-boron system. Now I am coming to the fifth case, which I called it as miscellaneous. Now this miscellaneous is further subdivided into topics, in which the very first topics come that we need to study the SN-NGP of sigma bond. CSIR net has not asked question on the basis of NGP of sigma bond, so it's very its probability of asking the question in the coming years is very high. So this topic for particularly for CSIR net for GATE is very important. Questions will be coming in the coming exams of CSIR net from particularly this topic. Now, once we have finished with this, we will be studying about NGP into, or we can say SN-NGP in larger rings. What does this larger rings means? Let's suppose you have a 8-membered ring, a very large size ring, and in this ring you also have a heteroatom present here. Let's suppose you have a sulfur atom and you have a group living group here. So how this sulfur is going to play an important role in neighboring group participation, this we will also be seeing in this part where we need to cover NGP in the larger rings. Now the case number 3 in a miscellaneous comes when we discuss the NGP of NOME group. I have shown you that this OME is little bit exceptional in characteristics. NGP of OME group. When we place this OME group at the beta center, the rate of the reaction is very slow as compared to the normal substrate. I have shown you into the comparison also. I don't think I would be having that comparison. I will be drawing it here again. Let's suppose we have a OME center present here and we have a OTS, that is a living group, present here, and we have a normal situation of OTS present here. We found that exceptionally the rate for the second substrate is high, though the beta center has a oxygen atom which can show an NGP mechanism. So this case also becomes very important. Yes, the NGP is possible, but it happens when we take this OME group farther away and place it at the delta position. If you have seen the previous lectures, you will be connecting this topic, or what I am trying to say, you will be connecting to that my words. Okay. Yes, it decreases to 400 times. Why it happens, and then what are the products when the NGP takes place, we will be seeing that from the same concept in the December, the net which held in December 2023. The question was asked from this concept only, and it was of 4 marks. Question was easy, but it was little bit lengthier in nature. So these are the things which we need to discuss, and there can be a small, there is also a small name reaction called as Demjanov and Tifnov-Demjanov reaction, which we can also cover in this miscellaneous part only. For the today's lecture, my focus is going to be on the concept which we say at NGP of sigma bond. Very important concept. Till now, no question has been asked in the past in CSIR NET exam or GATE exam from this concept. Yes, one time I think Maharashtra set has asked a question from this topic, but NET hasn't asked any question, GATE hasn't asked any question. So this topic becomes very important for the upcoming papers of the CSIR NET. Okay. If you are ready, then let's start with the NGP of sigma bond. There's a great depth in this topic. We will be going into the we will be seeing this topic into the depth, and how the questions can be asked, if it will be easy, if it will be tough, everything we will be covering in a holistic way. Yes sir, ready? Let's start then. We will write the heading as NGP of sigma bond. Let's take two scenarios. We have a norborane system present here. This was our norborane, and let's suppose I have placed a OTS group at an exo position, and we have a nucleophile placed here as ACOH, and we need to form the product P. Similarly, in the second scenario, what we have is a norborane system. Now this time I have placed my living group OTS at the endo position. The first scenario was for the exo, and the second scenario is for the endo. Now, first of all, we need to compare the rate of the reaction. We need to compare the products, whether the products are going to be same, different, and how they are going to look. So what do you think if I ask you this reaction goes via K1 rate and this goes via K2 rate? What's your views over this, whether K1 is going to be fast or whether K2 is going to be fast? Do share in the comments. What do you think? Very simple question, but has a great depth in this. This concept has a great depth. What happens when I look at the OTS group? It is present somewhere here. Now I need to find the bond which is anti to this red color sigma bond. If you carefully look into the norborane system, you will find this blue bond will be anti to the red bond of the OTS. How, sir? Let's suppose you have a sigma star orbital present at this center. You have a sigma star orbital. Now this sigma star orbital and the blue color bond are very easily approachable, and the sigma star and the sigma bond can attack into the sigma star orbital, and you can say they both are anti-periplanar also. Now what happens is the sigma bonds attack into the sigma star and the OTS group is removed. But if we look in the second scenario where we have an OTS at the endo position, now this bond is not in anti-position to the sigma star orbital or to this red color OTS bond. So it is not possible for it to attack into the sigma star orbital, and no other bonds are anti to this red color bond. So what happens is in the first scenario the reaction goes via an NGP path. So the rate, when we compare the rate of the reaction, we find that the rate of K1 is going to be faster as compared to K2. Sir, how the product is formed in the second scenario, I will be explaining that also. But first of all, we need to study the first scenario where I have placed the OTS at the exo position. Okay, let's see. We will see to it, Manisha, whether SN2 will be taking place or something else will be taking place. We will completely see the picture. First of all, let's deal with the first example where we have the OTS at the exo position. Now, I have distributed this concept into two levels. Level 1, when the question will be asked in part B, it means of 2 marks, and the level 2 will be of for the part C, when the question will be asked in 4 marks. See, first of all, we will discuss level 1 in order to build some understanding. We all know that ki yes, this blue color sigma bond is going to attack into the sigma star orbital, and of course this bond is going to break. So I will be not drawing this bond, and a new bond will be formed at this center. Since this has break from here, so I will be removing this sigma bond and we have a positive charge present at this center. Now, if you carefully observe this, what we find is it is actually a NOR-boron system in which the bridgehead centers has changed. Now, I will be drawing this black color carbons here. These are my bridgehead centers. Taking the help of numbering, when I move at this center, I have carbon number 1 and I have carbon number 2. Similarly, when I move from one black to another black via carbon number 1 and 2, this is going to be the path. And the carbons which are placed at the top center, let's suppose this green center is called as 3 and this green center is called as 4. Now I will be holding this 3 and 4 and I will be flipping this 3 and 4 little bit towards the right side. What I am going to observe is a red color bond which is going via carbon number 3, a red color bond going via carbon number 4, and coming back to the black center, the fourth number carbon has a positive charge also. Now let's suppose that this blue color carbon is present in the bridging center, so I have placed it at the top center here. So when I have rearranged, or I have just simply take the help of numbering and redrawn this structure, we find that yes, this is a NOR-boron system which a positive charge at the fourth center. Now what happens when the ACOH attacks? Since at this center we have hydrogen and hydrogen, the attack which will be preferable will be from the exo position, because the nucleophile does not want to go from the cavity. How a NOR-boron system looks like? See, let's suppose this is a book. If I open this book in this way, okay, so no nucleophile wants to come from this cavity. Are you able to get this concept? So similarly, a NOR-boron ring is present something like this, and no nucleophiles want to approach from this cavity. Hence, the attack will be from the exo position. So when I draw the product, they are going to look as a simple NOR-boron system where we have a OAC group attached at this center and a hydrogen will be present here. If the question is going to be asked in 2 marks, they will simply ask you how the product is going to look like. So you can draw the product. This is how the product looks. And if they ask you about the rate of the reaction, we can very comfortably tell that yes, the rate of K1 reaction will be faster as compared to K2. Why? Because in the case of K1 reaction, we have observed a sigma bond NGP. SN-NGP mechanism is taking place, that's why the rate is going to be faster. This concept will be asked for 2 marks only if they want to ask you this. Now, we need to go into a little depth also. The real picture is little bit different. Here also a concept of non-classical carbocation exists, so we need to understand that also. I will be explaining you first by my own, and then I will be giving you a reference of the book also. How books explain this concept, we will see to that also. But first of all, let's develop a understanding and see how this actually works. Okay, ACOH, yes, JACOH is acetic acid. Okay. Let's move ahead, and we will be moving into the level 2 of this question, when this question will be asked in 4 marks. Let's suppose examiner has asked us the intermediate which you are forming is either optically active or is either optically inactive. Then how we are going to answer this question? See, starting from the our substrate, we have a OTS bond present at this center. Now what is happening is this sigma bond is attacking into the sigma star and the OTS is getting removed. We see that a intermediate is formed, which is going to look like, since this bond has broken, I will be not drawing that bond. I will be just showing into a dash form. This is the scenario, and we have a sigma bond present at this center, since this new bond has been formed between these two centers. Now, if this is one of the intermediate, what I observe is the positive charge is going to be present at this center. Correct? Now, let's suppose I draw a second intermediate where I move this sigma bond back to the center where it was. So, the next positive charge which is going to be developed will be at which center? Let me draw. I have redrawn the bond back to its original state. Now I have broken this bond which was formed in the first intermediate. So I will say that now the positive charge will be formed at this center. Are you able to digest this thing or not? It's very important, because slowly and slowly the things are going to be more complicated. Yes, this example is complicated, but if we study this step by step, everything is going to be clear. See, first of all, what I have done is I have attacked into the sigma star orbital. The OTS has been removed. So this bond which is represented in dash was broken. So the positive charge is going to be at the center, which I have marked in the violet color. Now the solid line which was formed, I have moved that solid line back to its original state. The next positive charge will be formed at this center. Understood? Now, this was the first intermediate which is possible. This was the second intermediate which is possible. There is one more possibility, that I can bring this bond back to the sigma bond so that a kind of pi bond originate at this center. So what is going to happen is, we have actually a non-Boran system. The dash line represents the bond has been broken, and now a second dash line present at this center will also be forming, and this represents the formation of a new pi bond, and of course this bond here is also breaking. Let me represent this with a different color so that you don't get confused. This bond is also breaking, and the new dash line at this sigma bond is representing a formation of a new pi bond characters. Now, since I have moved this sigma bond at the position of the sigma bond where a double bond character is coming, the positive charge is going to originate at this carbon center. Are you able to understand these three different intermediates which I am trying to draw here? This is very important to understand. No book is going to explain you in this depth. I will show you how books explain these things. But it becomes very difficult for a student to grasp the concept in very depth. There comes the role of a teacher. What happens? I will be repeating once again. What happened? The first time we have attacked into the sigma star orbital, so the new bond has been formed at this center, which now I am representing in a black color. When I move this center back to its original state, here we have drawn a positive charge which will be at the this violet color center. And once I move this center back to the sigma bond position, at the sigma bond we will be having a double bond characters, and the positive charge is going to come at this center. So these are the three intermediates which are going to be formed, and why and when I try to draw a hybrid structure. What does a hybrid structure means? When I will be representing these all three structures into single structure, we will get to know about the intermediate. See how it's going to look like. We have a kind of NOR-boron system here. Now, sometimes the bond was present here. In few cases, the bond was present here, and in the few cases, the bond was present here. And very interestingly, the positive charge is now delocalized at this center, at this center, and at this center. So I can say that this positive charge is roaming at three centers. So can you tell me such type of carbocations are actually called as a classical carbocation or are called as a non-classical carbocation? The driving force, Dhaneshwari, was the initial stereochemistry where the sigma bond attacks into the sigma star orbital. That was the driving force. Understood? These all are the consequences, or we can say the result after the attack which is taking place. Of course, it means in this scenario also, examiner can ask you a question whether a classical carbocation is formed here or a non-classical is formed. You will be saying that very clearly, sir, at this center, a non-classical carbocation is formed in such a scenario. A non-classical carbocation is formed. Can you tell me this non-classical carbocation will be an example of 3 center 2 electron system or 3 center 4 electron system? This is all. This has a potential to be asked in exam, and again examiner can also ask you, tell me whether this is an example of 3 center 2 electron 4 electron system. How many electron system? Ohm Arya. Ohm is trying to ask, sir, how to know that whether a carbocation is a classical or non-classical? See, it's very simple, Ohm. If the carbocation is shifting from one center to another, like you do into rearrangements, like you study generally in the carbocation, that is the classical one. But when any carbocation is shifting at three centers, like in the NOR-boron case, like in this case, where you form a three center two electron system, it is going to be an example of non-classical carbocation. You need to take help of this three centered two electron system. How to imagine this three centers? See, you have these three centers which I am drawing in black in color, on which the carbocation is delocalized, and there are only two electrons which is roaming and between these three centers. I will show you that two electrons, they are present in this sigma bond. Sometimes they are present here, sometimes they are present here, sometimes they goes here, and sometimes they goes here. So these are the two electrons which are roaming in these three centers. So it make it clear that yes, the non-classical carbocations has been formed. Now, the question which was asked to me was whether the intermediate you have formed is optically active or inactive. Can you tell me this intermediate which we have drawn here is actually optically active or it is optically inactive? So please tell the name of other systems where non-classical we are dealing it, Anju. The previous case in the NOR-boron we have discussed one. Here we are discussing one. Slowly and slowly we will, when we will covering the syllabus, each and every cases where the non-classical will be coming, we will be dealing there and then only. Okay. So for now, you know the two cases. First was the NOR-boron system of simple when OTS attacks, and the second when the double bond and chimeric assistance took place, and the second scenario is now when a sigma bond NGP is taking place. Okay, move step by step. So what do you think? Whether it is optically active or inactive? So it becomes very difficult to imagine in such case because to find the plane of symmetry in this is little bit complicated. I will simplify this for you. When you look at this structure very carefully, you will see a 5-membered ring. 1, 2, 3, 4 and 5. Taking the help of this numbering, I will be redrawing this 5-membered ring here. Let's suppose this is going to be present like this. This is my 5-membered ring. I will be doing the numbering at this centers. Let's suppose this was my 5 center, this was my 4, 3, this is 2, and this is 1. Now, from the second center, what I have is a center like this, which we can say that, let's suppose this is carbon number 6 and a center present here, which is carbon number 7. So moving from the second number carbon, how we need to move it? I have moved little bit in this direction. This is my carbon number 6. Coming back downward, I have carbon number 7, and this carbon number 7 is attached with a dashed line to carbon number 5 and with a dashed line to carbon number 4. 5 and 4 also has a double bond character, and a positive charge is delocalized between all these three centers. Now it becomes very easy to identify whether this intermediate has a plane of symmetry or not. These both the structures are same. Now let's suppose if we take a plane and we cut the molecule in this way, it is going to be divided into two equal parts. It means we will say yes, plane of symmetry is present in this molecule. Did you understand this or not? Are you able to visualize how plane of symmetry is present in this molecule? Is it digestible for you or not? I'm telling you a really a concept in a great depth. Okay, this concept holds really a great depth. Now, since we have drawn a conclusion also in the previous lectures that whenever a intermediate is having plane of symmetry and is optically inactive, can you tell me, when I will be forming the products from this intermediate, what is going to be the relationship between the two products? You can tell me by just looking at the intermediate only. I have told you that I will be using that conclusion in the examples further also. Now it's time to use. Tell me fast, when I will be drawing two products. Let's suppose you don't know how the products are going to be formed, but you know what is going to be the relationship between the two molecules. Since the intermediate is optically inactive, you can straightforward tell me, sir, the products are going to have a relationship of pair of enantiomers. And since in the level 1 I have already shown you that one of the product will be like this, so if we don't know the mechanism in the detail also, at least we can for now draw the products also, how the products are going to look like. So I will be shifting to the next slide. If you have copied this, then tell me, I will be moving to the next slide. Should I move? Should I move to the next slide? See, when I pick my intermediate, which is like this, let me draw the 5-membered one, which we have rearranged and drawn. This is how our intermediate is going to look like. Now, when we draw the product from these centers, we get two products P and Q, and before drawing the products, we know that yes, the relationship between the two is going to be pair of enantiomers, and this is having a plane of symmetry, and this is of course optically inactive. How the product is going to look like? See, in the first scenario I have discussed that we will be having a nor-boron system and a OAC group will be present here. So if I need to just draw the mirror image of this molecule, which is non-superimposable, it is going to look like this. So we can very easily tell that how the P and Q product is going to look like. See, they both are mirror image and non-superimposable. It means they are pair of enantiomers. If we don't know the concept also, then also I can tell you this is going to be the product. Is it digestible to you? There is lot more left in this example, but before that, tell me, is this clear how we have reached to the P and Q conclusion? This is how the structure is going to look like. Now, whenever a pair of enantiomers are formed, whenever a pair of enantiomers are formed, there is likely 50% chance to form P and 50% chance to form Q. So I will be saying that they are going to be a racemic mixture, means final solution will be a racemic mixture, and of course racemic mixtures are optically inactive in nature. These can be asked in the form of statement also in the question, or they can ask, let's suppose they will ask you, they will give you the product and they will ask you whether the product is racemic mixture, it is optically active, inactive. These are the different ways in which they can ask question from here. So now it becomes very important to understand that yes, in this first scenario, when we have the OTS at the exo portion, we form racemic mixture as a product. The products are going to look like this. They are going to be pair of enantiomer of each other. Is it clear? If I show you the figure, let's suppose this is the scenario how a book explains this example. Have a look at this. What they are saying is they have an exotosylate example where the tosyl group is present at the exo position. Of course, this sigma bond is attacking into the sigma star orbital and this is getting removed. They have drawn this achiral intermediate. They have given directly this intermediate. They have not explained you how to reach at this intermediate. So this becomes very difficult for a student who is still learning to reach at this intermediate. But now, since I've explained you the concept in depth, you know how to reach at this center. Now they tell that you can attack at this center, at this intermediate, at the two centers, one at here and the second at here. In our intermediate, they were actually carbon number 5 and 4, which I can place here also. This was carbon number 5 and this was carbon number 4. You can understand from here also, and if it feels you little complicated, then you can apply the straightforward concept. Yes, they are going to be pair of enantiomer. Yes, the first structure looks like that. It will be the mirror image of the first structure, so you can very easily identify the P and Q product. But we will see how the book explains this concept. When we attack at the carbon number 5, the bond actually forms at this center and you have an OAC group present here. When I rearrange this norborane system, what I find is a product which looks like this. And when we attack at, let's suppose, carbon number 5, the bond actually forms at this center and the product is going to look like this. And they found that yes, they are mirror image of each other, so the product is going to be a racemic mixture. This is what I have explained you in the previous slide. Are you able to digest the whole concept which I am showing here? Is it digestible to you or not? It's very important concept, and good to know that it is not asked in CSIR NET exams till date. So the probability of getting asked in the incoming exams becomes very high for this concept. So when we are dealing with an exo case, the intermediate is going to be achiral, products are going to be pair of enantiomers, the final solution is going to be racemic mixture. No doubt should be present here in this first example. So I will be moving on the second case when I have this tosylate group at the endo position instead of the exo position. Should I explain the second scenario? Are you clear with the first one? Is it completely digestible to you? This is how the book explains you. Thus, they simply say that when we add the when we add the nucleophile, what they are saying that add a deprotonate. Okay, they are saying that when we attack and we remove the H plus of the OAC, the product is going to look like, and when they attack at the fifth center, the product is going to look like this. Clear? Very good. Now let's move to the second scenario. I will be coming to these statements also because some of the students says that we need some theory also, sir, to understand the things. You can note down that this also, but let me explain the second scenario first. In the second scenario, it is also very important. Sometimes students get confused here and they simply tell that SN2 mechanism is going to take place. Understand this concept. It has also a real depth in here. What we have is a OTS group present at the endo position and the ACOH group is present here. What book says is, once the OTS group, since the sigma bond NGP is not possible here, no bond is present in anti to this red color bond to attack into the sigma star. What happens? This OTS, being a living group, can be removed by its own. So once it is get removed from here, you are going to generate a carbocation at the center. It is a normal carbocation which you deals in the chemistry, in the more of the intermediate part, I can say. When you deal with the intermediate carbocation, this is a very normal carbocation which is called as classical carbocation. So in the endo case, first of all we form a carbocation which is called as classical carbocation. Now this classical carbocation sees an opportunity to convert itself into a non-classical carbocation. Why? Because a non-classical carbocation, the positive charge is roaming at three centers. Of course, it is going to be little bit more stable as compared to this. So what happens? Again, this bond present at this center is going to rearrange to this center, and again the scenario is going to look like what we have discussed in the previous case. Now a bond is going to be formed here and the positive charge will be formed here. So again, when I move this bond to this center, positive charge can arise here, and when I move to the bond to this center, the positive charge can arise here. I am not drawing these three intermediates separately because I have done in the previous case. And once I draw a resonance hybrid structure, I can say a hybrid structure where all the three forms are present in a single structure, what we have is a dashed line present at this center, a dashed line present at this center, and a dashed line present at this center. And the positive will be roaming at the three centers. We can say sometimes the positive is here, sometimes it is here, sometimes it is here. It means it has been converted into a non-classical carbocation. It means the carbocation formed first was a classical one, and then it has been converted to a non-classical carbocation. We have gone into the depth of this concept that when a non-classical carbocation forms, the product from this center is going to be a pair of enantiomer, what we have just discussed in the previous example. How the products are going to look like? See, one of the product will be where OAC will be present at the exo position, and the second pair of enantiomer will be formed, and it is going to look like this. So these are the products P and Q which is forming from the non-classical carbocation. Clear, sir? It means the products are going to look similar in both the cases of both the cases, one in the exo also and one in the endo also. But there exists a little difference here. We say that the racemic mixture formed in the first case, we say that the racemic mixture formed in this case is 100%. It means overall solution is a racemic mixture. It is overall optically inactive. But when we are dealing with the endo situation, the experimental facts say that here the racemic mixture which we have formed from the non-classical carbocation is approximately 90%, and if I go more exact, it is close to 93%. So where does this 7% has gone? See, you need to understand very carefully. Since in this example, first of all, a classical carbocation was formed, there were so few products were also observed from this classical carbocation. If I draw the product from this molecule or from the classical carbocation, how the product is going to look like. We will be having a OAC group which will be present at the exo position. Now, if you understand the concept of enantiomeric axis, then you will be very easily getting this concept. I say that this molecule has a enantiomeric axis close to 7%. Or in order to simplify these things, what I am going to take is, I will be taking that it is close to 90% and it is close to 10%. Now it becomes very easier to understand. See, so I am telling that when I have placed my OTS group at the endo position, 10% is the enantiomeric axis and 90% is the racemic mixture. Since a classical carbocation was formed in the starting, some of the products has resulted from the classical carbocation and they were at the exo position. It means in this overall solution, the the exo position OAC group product is more in amount as compared to that of the second enantiomer, I can say. What is happening in this racemic mixture? We have 45% this P enantiomer and 45% we have this Q enantiomer, and the rest of the 10% exo we have observed from this center. So I can say that this molecule, this overall solution will be optically active, and this will be because of this 10% enantiomeric excess or the 10% excess amount present for this particular P enantiomer. Are you able to digest the concept what I am trying to say? If you want, I can say and repeat this concept in Hindi also. Yes, do tell me. So when we have these our substituent, that is OTS, the living group at the endo position, what we observe is 10% enantiomeric excess product is formed for the and form for this case, and 90% is the racemic mixture. If you go more exact, the data says that it will be 93 and it will be 7%, but you need to understand the concept. So I will be repeating this concept once in Hindi also for the so that everyone gets this concept. See, जब भी ओटीएस ग्रुप एंडो पोजीशन पे लगा होता है तो सबसे पहले एक क्लासिकल कार्बोकटायन बनता है। क्लासिकल कार्बोकटायन से भी कुछ प्रोडक्ट बन जाते हैं और वो प्रोडक्ट आपको ऐसा दिखता है जैसा मैंने बनाया है। क्लासिकल कार्बोकटायन अपने आप को एक नॉन क्लासिकल कार्बोकटायन में तब्दील कर लेता है और यहां से हमें 90% प्रोडक्ट मिलता है जो कि 90% रेसमिक मिक्सचर होता है। प्रोडक्ट्स कैसे दिखते हैं, उनकी फोटो कैसी होती है, वो मैंने पिछले केस में ही एक्सप्लेन किया था, तो कॉपी पेस्ट करके यहां लिख दिया सर। तो इस पूरे सोल्यूशन में हमें ऑब्जर्व क्या होता है कि हमारे पास 90% तो क्या है रेसमिक मिक्सचर और 10% क्या है एनेंशियोमरिक एक्सेस। एनेंशियोमरिक एक्सेस का मतलब एक्सेस अमाउंट में प्रेजेंट ये वाला फॉर्म जिसको मैं पी फॉर्म कह रहा हूं, ये थोड़ा उसको रिजेंबल करता है, तो ये थोड़ा ज्यादा अमाउंट में प्रेजेंट है। समझ पा रहे हैं आप? अगर मैं इस पूरे सॉल्यूशन में आपसे पूछूं कि बताओ P कितना परसेंटेज होगा और Q कितना परसेंट होगा, कैन यू टेल मी? इफ I have taken the total solution, tell me what is the percentage of P and what is the percentage of Q? Can you explain me if I ask you in the total solution? इससे पता लग जाएगा कि आपको कितना समझ में आया है और कितना समझ में नहीं आया। Tell me the total percentage of P and the total percentage of Q. जल्दी बताइए। वेरी गुड। अगर हम टोटल परसेंटेज चेक करें देन सर द पी इज गोइंग टू बी प्रेजेंट इन 55% एंड द क्यू विल बी प्रेजेंट इन 45%। The 45-45 forms a racemic mixture, and the 10% excess is responsible for the enantiomeric excess. And from where this 10% has came, so this has came from the classical carbocation. इफ अगर आप इस कॉन्सेप्ट के डेप्थ को समझते हैं, एग्जामिनर कितना भी घुमा दे क्वेश्चन को, आप डेफिनेटली आंसर करके आएंगे। अब आज के बाद से इस कॉन्सेप्ट पे पूछा गया सवाल गलत नहीं करेंगे, वादा करिएगा इस बात का। आपको थ्योरी भी थोड़ी बहुत दिखा देते हैं, यू कैन हैव अ लुक एट द थ्योरी ऑल्सो। ये भी यही बात कहती है, ड्यूरिंग द एसिटोलिसिस ऑफ एक्सो एंड एंडो नॉन ब्रोनिल टोसाइलेट, एक एक्सो और एंडो का जब हम एसिटोलिसिस रिएक्शन करते हैं, तो जो एक्सो होता है वो 350 टाइम्स फास्ट रिएक्शन दिखाता है एज कंपेयर टू एंडो। आप जानते हैं, इन द फर्स्ट सिनेरियो देयर वाज एन एनजीपी मैकेनिज्म of sigma bond, in the second it was not, that's why it is taking place in the endo isomer. Both the isomers gives only, दोनों के दोनों आइसोमर्स एक्सो एसीटेट का ही प्रोडक्ट मेजर दिया करते हैं। दोनों के प्रोडक्ट्स की फोटो एकदम सेम टू सेम होती है। एंड ऑप्टिकली प्योर एक्सोटोसाइलेट गिव्स 100% रेस्पिक मिक्सचर। कह रहा है जब आप एक्सोटोसाइलेट लेते हैं यू गेट 100% रेस्मिक मिक्सचर। याद करिए, वही तो मैं चीख चीख के पढ़ा रहा हूं। वाइल द ऑप्टिकली प्योर एंडोटोसाइलेट, जब हम एंडो के पास पहुंचते हैं तो 93% ये एक्सो एसिटेट देता है, 93% रेस्मिक मिक्सचर मिलता है। क्या ये पहला पैरा आपको समझ में आ रहा है? ये वही चीजें हैं जो मैं कब से चीख चीख के पढ़ा रहा हूं, बस लैंग्वेज में लिखा हुआ है। कोई नया बच्चा होता है, when the student is still learning, it becomes difficult for him to understand all these concepts. सेकेंड पैरा भी यही सारी बातें कहता है। द एक्सो आइसोमर द 1,6 बॉन्ड इज सुटेबली लोकेटेड एट द नेबरिंग ग्रुप टू द लीड टू द एनचाइमेरिक असिस्टेंस बाय द बैक साइड अटैक। यही कह रहा है, सिग्मा बॉन्ड की एनचाइमेरिक असिस्टेंस लगती है, इट अटैक्स इनटू द सिग्मा स्टार ऑर्बिटल एंड नॉन क्लासिकल कार्बोकटाइन की फॉर्मेशन होती है, which is more stable than the कार्बोकटाइन, जो कि क्लासिकल कार्बोकटाइन से ज्यादा स्टेबल हुआ करता है। These are the things they are trying to explain. You can have a reading of this para also. They are explaining you the same thing in order to have a great if you want to relate this, want to see the figures they from which they are explaining, you can refer to PS Kalsi also, or just have a reading of this. And what I have told you, the points in this example are important. I hope this NGP part is clear, and I have discussed each and every point of the sigma bond NGP. Now in the coming lectures, we will be coming up with few questions and few concepts. For today, I am winding up the lecture here only. Thank you so much. Take care. Bye bye. Let's meet tomorrow again at 9 a.m. I hope you are enjoying this lecture series. You are learning new concepts in a new way and in an easier way. See, sometimes this concept become very typical if you try to study from books and if you try to study on your own. But if someone helps you a little bit, it becomes easier. So now you can understand this concept very easily in a great depth. Thank you so much. Take care, and we will meeting again tomorrow at 9 a.m.